Rational functions. A rational function is of the form f of x divided by g of x, where f of x and g of x are polynomials, and g of x cannot equal 0 since it's in the denominator. For example, r of x equal to 3x minus 4, a linear function, divided by x squared minus x minus 12, a quadratic function, is an example of a rational function. The domain of a rational function, f of x divided by g of x, is all real numbers except those that make g of x, the denominator, equal 0. So in this first example, let's find the domain of 3x minus 4 over x squared minus x minus 12 and write our answer in interval notation. So we need to find the values that make the denominator x squared minus x minus 12 equal 0. Well, this is solving a quadratic equation, so we can try to factor it, and it does factor to x minus 4, x plus 3 equals 0. And by the zero product property, if we set the first factor equal to 0, we get positive 4. If we set the second factor equal to 0, we get negative 3. So these are the two values we need to exclude from the domain. So in interval notation, the domain is all x values in the interval from negative infinity to negative 3, not including negative 3, so we use open parentheses, and we pick up right outside of negative 3 and head all the way to 4, again not including negative 3 or 4 using open parentheses, and picking up again right after 4 and heading all the way to positive infinity. Let's take a look at the rational function 1 over x, known as the reciprocal function. Having a good understanding of 1 over x is going to help us later when we graph our more complicated rational functions. So here's its graph and its corresponding xy table. So if I substitute in, say, negative 3, I'd get negative 1/3, and that goes with the coordinate point, of course, negative 3, negative 1/3. If I substitute in 0, 1 divided by 0 is undefined, so that means along the y-axis where x equals 0 there is no corresponding coordinate point. And if I substitute in 2, let's say, I'd get 1 divided by 2, so that corresponds to 2 1/2. And that's just substituting in some nice numbers. We can substitute in, of course, any numbers. So let's say we substituted in a half. So if I substitute a half into this x, what I'd have is 1 over a half, which of course I'd multiply by the reciprocal, so we have the value 2. So at 1/2, the value that comes out is 2. So at 1/3, the value that would come out is 3, and at 1/4, the value that would come out is its reciprocal, 4, and so on. So we can see that we're getting closer and closer to the y-axis here. And as we substitute in bigger and bigger values, we're going to get closer and closer to the x-axis here. And that takes us to some of the properties of this reciprocal function. So we have the domain and range. Of course, the domain is everything except 0. We can't plug in 0 or we get undefined. Our range is also everything except for 0. So if I look at the graph, 0, the x-axis, is skipped over. My graph doesn't actually intersect the x-axis, it just approaches or gets close to it, but doesn't actually intersect it. And my graph is decreasing over its entire domain, so I'm decreasing from negative infinity to 0, and from 0 to infinity. There is origin symmetry on this graph. I can rotate it 180 degrees about the origin, so it is an odd function. And then we also have these asymptotes. So a vertical asymptote on this graph is x equals 0. That's the vertical asymptote. And what it means is that my graph is approaching. It's getting close to the line x equals 0, which is the y-axis. So I can see that up here along the graph, my function is approaching the y-axis, getting close to it, going towards positive infinity as I started plugging in values closer to 0. So when I plugged in 1/4, I got 4. If I plug in 1/5, I'd get 5. So I'm getting really close to the y-axis because my values are just getting bigger and bigger and bigger. And on the other side of the y-axis, as I approach 0 from the left side of 0, now my function is going towards negative infinity. So this y-axis, x equals 0, is called an asymptote because my function is approaching it with its values. And my horizontal asymptote is y equals 0, or the x-axis, because again, I am approaching the x-axis. As I start to substitute in larger and larger x values, I'm going to get closer and closer and closer to that x-axis, both on the left side and on the right side. So on both sides, I'm getting closer and closer to y equals 0. We also want to have a good understanding of 1 over x squared. So again, here is the graph and the xy table of values. So substituting in -3 into the denominator, I would of course get a positive number, so I'd get 1 over 9. So at -3, I'm at 1/9. If I substitute in 0, I get undefined again, so I have no values along the y-axis. And let's say I plug in 2, the denominator is 2 squared, so I'd get 1 over 4, so I'd get 2 1/4. And so looking at its properties, well, its domain is everything except 0. But this time its range is from 0 to infinity. So once again, I never cross the x-axis, but I'm actually never even below it either. So my range is only values that are positive above the x-axis. I'm increasing from negative infinity to 0, and I'm decreasing from 0 to infinity. There is y-axis symmetry here, so this is an even function. And once again, the vertical asymptote is x equals 0. So the y-axis, x equals 0, is the vertical asymptote. And my function this time is approaching positive infinity on both sides of that vertical asymptote. So 1 over x squared had the same asymptotic behavior near the asymptote. Both sides are going up towards positive infinity. And my horizontal asymptote is the x-axis, y equals 0. So again, I'm approaching 0. I'm getting really close to it. I know it kind of looks like it intersects it, but it doesn't. It's just getting really close to it. Because if I think about substituting in 5, I'd get 1 over 25. If I plug in 10, I'd get 1 over 100. So I'm getting really close to the x-axis, but I'm not actually going to intersect it. Let's take a closer look at asymptotes now. An asymptote is a line that a function approaches or gets arbitrarily close to at the ends of a function. So it's not actually part of the graph, but it's a guide to drawing the graph. And we have 3 different kinds of asymptotes. Horizontal asymptotes, so they're of the form y equals a. So we can see that it's sketched as a dotted line because it's not part of the function. It's just a guide to help us drawing the function. I can see that both sides get close to this particular horizontal asymptote. And to describe what's happening, we'd use this notation as x values go to positive infinity. So remember, positive infinity is over here. F of x, or the y values, are approaching some real number. So in this case, they're approaching the number 1. And the same thing is happening towards negative infinity. As x values approach negative infinity, f of x, the y values, get closer to some real number. And again, that number is 1. Another side note, a function can intersect a horizontal asymptote, but it doesn't have to. A vertical asymptote is of the form x equals b. A vertical line is x equals. So here it is, a dotted vertical line at the x value -2 in this image. And we would say that as x approaches a real number from one side, so let's say I'm approaching -2 from its left side. So I'm on the left side of -2. I'm approaching infinity. F of x, the y values, are going to either positive or negative infinity. So on the left side of -2, my y values are approaching positive infinity. On the right side of -2, my y values are approaching negative infinity. Now, what's important about vertical asymptotes is a function cannot ever intersect a vertical asymptote, because these are places that make the denominator equal 0, and that means that we have to be undefined there. So it's not possible, we cannot intersect a vertical asymptote. And the last type of asymptote is called a slant or oblique asymptote, and it's a linear function. So here I have this dotted line as my slant asymptote. It's actually y equals x in this example. So what's happening is as x values approach positive infinity, so as x values are getting bigger, y values, f of x values, are approaching, this arrow means approaching, this line. So I can see I'm getting close to this dotted line here. And same thing as x values approach negative infinity, my y values are getting close to this line, right? They're getting really, really, really close to this line, and we can intersect a slant asymptote. It is possible, but it doesn't have to happen. In this example, using the graph, we want to identify the domain and range and write it in interval notation, and we want to identify from the graph all the asymptotes. So let's go ahead and start with domain here. So the domain of this rational function, based on the graph, it looks like we're skipping over -2, so there's no values along the x value -2, and there's no points, no values along the x value 3. So my domain is going to be x in negative infinity to -2 open, and -2 to 3, and 3 to infinity. So we're just skipping over -2 and 3. So we can see that there is a part of the graph everywhere else. The range of this function, well, the y values look like they're going to go from negative infinity all the way up to 0. And since there's a point there, the y values do include 0. So we're going to go negative infinity up to 0, including 0. But then there's this gap. There's no y values between 0 and 1. And we're not intersecting 1. I'm just approaching 1. So I'm going to not include 1, so use open parentheses, and we are going to continue all the way up to infinity for my y values. And now we're going to go ahead and list the horizontal asymptote. So the horizontal asymptote is the line y equals, so it's important to write y equals since it's a horizontal line, y equals 1, this dotted line. And then the vertical asymptotes, there happens to be 2, have to be x equals, so x equals -2 and x equals +3. So just a quick warning, make sure that we never end up doing something like this, writing out HA equals 1. So we don't want to do that. We have to write y equals to express that it's a horizontal line, and x equals to express that it's a vertical line. Now these table of values over here are just really trying to emphasize the idea of what an asymptote is. So what's happening is that as I plug in bigger and bigger x values, so you can see that my x values here are getting bigger towards 1,000,000, what's happening to the y value? So this is my function, x squared over x squared minus x minus 6. So substituting in these x values gives me these y values. And notice that they're getting closer to 1. So we have 1.1, 1.01, 1.001, and this last one is really, really close to 1. So as my x values are going towards infinity, right, as they're heading towards infinity, my y values are getting closer and closer to 1. And the same thing if I did plug in values over here like -10 and -100 and -1,000,000, I would see that those y values are still getting closer and closer to 1. So that's understanding numerically a horizontal asymptote, and let's understand numerically a vertical asymptote. So if I substitute in 3.1, so what are we talking about? We're talking about plugging in a value to the right of 3. So I know this is further over, but I'm plugging in 3.1 and then 3.01 and 3.001. So that's what's happening on this table is I'm getting closer to 3.00001. And what I can see is happening to these values, so as my x values get close to 3 from the right side of 3, my y values are getting huge. So they start out at 18 and then they're at 180,000. And that tells me that I'm heading towards positive infinity. So as I start to plug in those numbers into my function, that's the behavior, the asymptotic behavior on the right side, is that the right side goes up to positive infinity. And then if we analyze the left side's going down to negative infinity. So that actually is something that we should take a close look at on this graph and really understand what's sort of happening here. So this vertical asymptote here comes from setting the denominator of this function equal to 0. So there's two factors here, x minus 3. If I set that equal to 0, I get this positive 3 out. That's how I get out this vertical asymptote. And this factor, it has a multiplicity of 1. It's x minus 3 to the first. And what I want you to remember is the graph of 1 over x, just x to the first, because near that asymptote, it had asymptotic behavior that went in opposite directions. One side heads up and the other side heads down. And the other vertical asymptote on this graph comes from this factor, x plus 2 to the first. The multiplicity is also 1. So negative 2 is a vertical asymptote because the denominator had a factor when set equal to 0 that gave us negative 2. And I want you to notice, since its multiplicity is 1, it too has opposite asymptotic behavior. One side goes towards positive infinity and the other side goes towards negative infinity. As opposed to, let's say we had a factor in the denominator that was, I don't know, x plus 4 squared. So that factor was in the denominator. Since the multiplicity is 2 there, the asymptotic behavior is going to go in the same direction. So we'd have negative 4 is a vertical asymptote. And the behavior is that either both sides are going to go the same direction towards positive infinity, or the other option is that both sides are going to go down towards negative infinity. So that's dependent upon the multiplicity. Let's go ahead and find all asymptotes of each function, and we're going to write them as equations of lines. So this time we have the equation of the function, not the graph. So how are we going to do this? So to find asymptotes given the equation for a rational function, well, we need a rational function in lowest terms. To find the vertical asymptotes, we're going to solve when does g of x, the denominator, equal 0. So that means that we're going to have to factor the denominator in this example. So the numerator is 3x. The denominator is going to factor to 3x minus 4 and x plus 1. So to find vertical asymptotes, we set the denominator equal to 0 as long as we're in lowest terms. So no factors canceled, we have lowest terms. So if I set 3x minus 4 equal to 0, I get positive 4/3. And if I set x plus 1 equal to 0, I get negative 1. And we can leave them like this. In fact, we have to leave them like this. They are vertical lines, so they are x equals. So now what we're going to do is try to find any horizontal asymptotes or slant asymptotes. So to find horizontal asymptotes, we compare the degrees of f of x and g of x. So the degree meaning compare the highest power of x in the numerator to the highest power of x in the denominator. So looking at our example, our numerator is to the first power, so 3x to the first, it's linear, and our denominator is 3x to the second, so it's quadratic. So let's see what happens. Well, if n equals m, if the degrees match each other, then y equals a over b is the horizontal asymptote. So that means the leading coefficient over the leading coefficient. Well, they're not the same in our example. The top is 1 and the bottom is 2. So if n is less than m, so if that means if the top is less than the bottom, which is what we currently have, then y equals 0 is the horizontal asymptote. then y equals 0 is the horizontal asymptote. So what's happening here is if we were to plug in values, so we're not actually being asked to do this, but if we were to plug in bigger and bigger values into our function, into our y equals, so in that previous example, like how we plugged in 10 and then plugged in 100 and 1,000 and 1,000,000, what's going to happen is that our y values are going to get really small. So they're going to end up being numbers like 0.000 something. So they're going to get really, really small, and they're going to approach 0. So instead of having to plug in bigger and bigger numbers, we can use, this is essentially a shortcut, just compare. If the degree on the bottom is bigger than the degree on the top, then the whole fraction is going to go to 0. So our horizontal asymptote is just y equals 0. Let's try this one again. Find all asymptotes of each function, write as equations of lines. So to find vertical asymptotes, we set g of x, the denominator, equal to 0. Well, we have to factor the denominator, but to make sure we're in lowest terms, we also have to factor the numerator. So we have a difference of squares, x minus 1, x plus 1 from the numerator. In the denominator, if we factor out that 2, we'll get x squared minus 4, which is another difference of squares, so we get x minus 2, x plus 2. So there are no factors that cancel, so this is in lowest terms. To find vertical asymptotes, we set the denominator equal to 0. Well, we can't set 2 equal to 0. That doesn't make sense. So we set our factor of x minus 2 equal to 0 to get x equals positive 2. We set our factor of x plus 2 equal to 0 to get x equals negative 2. So those are our vertical asymptotes. And to find horizontal asymptotes, remember, we compare the degrees. So looking at our original function here, well, the degree of the numerator is 2, and the degree of the denominator is 2. So this time we are under this situation if n equals m, if those degrees match up, right? N equals m. Then y equals a over b, so that's the leading coefficient over the leading coefficient, is the horizontal asymptote. So for us, our leading coefficient is 1, and of the numerator, and of the denominator it's 2. So those numbers in front of those x squareds. And that would mean that our horizontal asymptote is y equals 1 over 2. So one more example of this, finding all the asymptotes of the function. So my function this time is x squared plus 1 over x minus 2. So thankfully it's already in lowest terms. We can't factor any further. So to find vertical asymptotes, we set the denominator g of x equal to 0. So to find the vertical asymptote here, we're going to set x minus 2 equal to 0 and get x equals positive 2. Now, to find horizontal asymptotes, we're going to compare those degrees. So in the numerator, we have x squared. In the denominator, we have x to the first. So the case that we're falling under here is this one. If n is equal to m plus 1. So essentially, this is saying if the top degree is bigger, but by exactly 1. So 2 is bigger than 1 by exactly 1. It's 1 bigger than the denominator's degree. So if that happens, in that case, we then have an oblique or a slant asymptote there. So we don't have a horizontal asymptote, we actually have a slant asymptote. And so how do we find it? Well, it's the linear quotient after long division. So what we're going to have to do here is we're going to have to do some long division. Well, we're going to divide the rational function. So the rational function is essentially division. X minus 2 is going to be divided into x squared plus 1. So if we remember long division here, we focus on the x, and we think about x times what gets us x squared? Well, x times x. And then we multiply. Well, x times x is x squared, and we multiply x times negative 2. So we get minus 2x. And then we subtract this quantity, so it's going to change this sign and this sign. And then we go ahead and add down. Well, x squared minus x squared will cancel, and we get 2x plus 1. And then we do it again. So we think about, okay, x times what gets me to 2x? Well, that's just 2. And then if we do that one more time, we get 2 times x, that's 2x. And then 2 times negative 2, that's negative 4. And we would subtract those quantities, so change the signs, and we'd get out a 5. Well, we actually don't care about the rest of this part. It says to find the quotient after long division. So the quotient is just this portion up here, this x plus 2. So the slant asymptote, it turns out, is just y equals x plus 2, which is linear, right? It's of the form mx plus b. So it's only the quotient part. We don't actually care about whatever the remainder is. It's just the quotient part that we're interested in. And we'll just take a look at the last case. So the last case says if n, so that's the power on the top, right? If n is greater than m plus 1. So that means if the degree on the top is actually bigger, more than 1 bigger. So if the top was like x to the 4th and the bottom was x squared. So it's not bigger by exactly 1, it's bigger by exactly 2. So when that happens, there's not a horizontal or an oblique asymptote, and the end behavior will resemble this power function here. So it's kind of got its own unique formula. So this is not necessarily super common to the ones that we will see, but the formula is there for our reference. Alright, we've reached our big examples. We want to graph more complicated rational function. We have x plus 1 over 2x squared plus 5x minus 3. And we're going to follow this sequence of steps here. So we're going to factor the numerator and denominator and find the domain. So the numerator is just x plus 1, nothing I can do there. The denominator will factor to 2x minus 1 and then x plus 3. So let's go ahead and find the domain. Well, the domain is going to be everything except the values that make the denominator equal 0. Well, the value that will make this first piece equal 0 is 1/2, and the one that will make the second piece, the second factor, equal 0 is negative 3. So the domain is negative infinity to negative 3, and then negative 3 to 1/2, and 1/2 to infinity. So we want to get to a point where we can look at the factor and just think about the value that makes it equal 0. So this one would be 1/2 and this one would be negative 3, and we're simply removing those values. Now, the factored version is in lowest terms, so we don't have to worry about the second part. Alright, so now what we're going to do is find and plot the x-intercepts on a graph by setting y equal to 0. So we still want to find the x-intercepts and the y-intercepts of even a rational function. So to find x-intercepts, of course, we're going to let y equal 0. Well, that's f of x. So we're going to set f of x equal to 0. So we set 0 equal to x plus 1 over 2x squared plus 5x minus 3. Well, if we multiply both sides by the denominator, we essentially are just solving when does 0 equal x plus 1. Well, if I subtract the 1, I get negative 1. So to find x-intercepts, it's really like just setting the numerator equal to 0. So as a coordinate point, of course, it's negative 1, 0. And we'll plot everything on the graph at the end. So part 3 is find and plot the y-intercept by setting x equal to 0. So to find our y-intercepts, we set all of our x's equal to 0. So that's, you know, here, here, and here. So if we set all of those x's equal to 0, all that's left is 1 over negative 3. So that means our y-intercept is 0 negative 1/3. So again, I'd want to avoid, having to show this work. We can just see substituting zeros into these x's will give us 1 over negative 3 left over. So it's easier to plug it into the original one versus the factored one. And now we move on to finding the vertical asymptotes by setting that denominator equal to 0. So we actually have already done that and thought about that on this example when we found the domain. So our vertical asymptotes, if I set the first denominator's factor equal to 0, I get x equals 1/2. And if I set the second denominator's factor equal to 0, I get x equals negative 3. And then part 5, find and graph those horizontal or oblique asymptotes. It's one or the other. So if we compare, well, the numerator has a degree of 1 and the denominator has a degree of 2. So when the numerator is less than the denominator, then our horizontal asymptote is y equals 0. So these are all of the parts that we want to have before we start to go ahead and put everything on a graph. So we're going to go ahead and move on to step 6 here, because this part says if the graph has a non-zero horizontal asymptote, there's something else we'd want to do, but our horizontal asymptote is 0. So we're going to go ahead and complete the graph by plotting everything and trying to piece it together. Alright, here we go. Let's plot everything on this xy plane. So our x-intercept, the only place where our graph is going to cross the x-axis, is at negative 1. So what I'm going to do is I'm going to go ahead and take the factor that came from and put it directly above the x-intercept. So x plus 1 to the first, this factor from the numerator, is what gave us that x-intercept of negative 1. And then the y-intercept is 0, negative 1/3. So that's about right here, right? That's about negative 1/3. And then I'm going to go ahead and graph my vertical asymptotes. So my vertical asymptotes happen at x equals 1/2. So 1/2 is right here, that x value 1/2. So I'm going to go ahead and draw myself a vertical asymptote at x equals 1/2. And on the bottom, I'm going to put what factor this came from. This came from 2x minus 1 to the first power. So that's what factor this vertical asymptote of x equals 1/2 came from, was 2x minus 1 to the first power. And my other vertical asymptote over here at negative 3 came from the factor x plus 3. So I'm going to put that factor down here. And that was to the first power as well. So right now I've plotted everything that I have. These are the only 2 points that I currently have. And then I have these asymptotes, and the horizontal asymptote finally goes through y equals 0, which is the x-axis. So what we want to remember is that we have to approach these asymptotes. That's why they're important to rational functions, is that we get close to them. So when I'm trying to construct the rest of my graph, I have options. So let's remember the domain. This graph has to exist everywhere except negative 3 and 1/2, right? So it's got to exist, on this side, in the middle here somewhere, and on the right here somewhere. So there's going to be 3 pieces to my graph. So I can think about these vertical asymptotes as breaking me up into pieces. So I'm going to have 3 pieces in between those 2 vertical asymptotes. Now, I'm going to go to the part where I have some information. I have some points on the graph. I have this point at negative 1 and this point at negative 1/3 on the y-axis. So since x plus 1 to the first power was the factor that gave me my x-intercept, because the multiplicity is 1, as we know from previous sections, we would cross or cut through the x-axis at that x-intercept. So that rule sort of still applies. So the behavior through -1 is I'm going to cut straight through at -1. And if I know that I have to go through this other point, this other y-intercept, that would mean that my graph has to look something like this. So I'm going to go ahead and connect these 2 points together. Well, whoops. Be really careful about this. I'm going to connect these 2 points together, and then I'm actually going to continue, and I know that I cannot cross a vertical asymptote and I have to approach it. So that means that I didn't do a good job of crossing it, but it does cross. I'll just make this point bigger. It does cross that vertical that x-intercept right there, and it approaches this vertical asymptote. So I know that this is the general shape of my graph. And because I have to approach this asymptote here, if I pick up where I left off, I have to head up and I have to approach this asymptote up here because, first of all, I can't turn around, right? I can't go this direction because I'd be cutting through the x-axis and there's no other x-intercept. So that's why I would have to approach up towards positive infinity. I'd have to get closer to this asymptote towards positive infinity. So right now I have a part of the graph. I know that it also has to exist on the left side of -3 and over here on the right side of 1/2. So I've gotten further, but I'm not done yet. So now what I'm going to do to finish the graph is I have some choices. I can always plug in points. But that's tedious, and we don't want to have to do that. Sometimes we will have to do it if we don't have enough information. So how that would work is I would take any value over here on the left side, so I'd say, let's say -4, and I would just substitute it into the original function or the factored version, and I'd see what value comes out. And that would help determine where this graph is going to be. So let's talk about the two options for this left part of the graph. My graph is either going to look something like this, where, whoops, man, it keeps doing that. So it's either going to look like this portion here, where I approach, again, I have to approach these asymptotes. So I'd have to get close to the x-axis over here, and I'd have to get close to this vertical asymptote up here. That's one option. The other option is it could look like this. It could be down here, because this is another way I'm still approaching those asymptotes just from the underneath the x-axis, and then I'm heading down towards this one. To be clear, it cannot be both pieces. Do not leave both pieces, because this doesn't pass the vertical line test. This wouldn't be a function if I left both pieces. So we have to decide which one it is. So to decide which piece it is, again, I could plug in a number. I could plug in -4, see what comes out. If I get a point above the x-axis, then it's going to be this piece. If I get a negative value, I'd be this piece below the x-axis. But I want to give you sort of an even quicker way of doing this, of figuring out which one it is. So the way that I'm going to do it here is I'm going to use the vertical asymptote behavior. So this asymptotic behavior. So that's why I put x plus 3 to the first. That's why I put it below where it came from. This -3 came from this factor, x plus 3 to the first. And what I'm remembering here is that when an asymptote has a multiplicity of 1, then it's going to behave like 1 over x. And 1 over x had one side of the asymptote going to positive infinity, then the other side had to go towards negative infinity. So one side went up here, and the other side would have to be heading towards negative infinity. So that means that it would have to be that version that was below the x-axis and still approaching each of those asymptotes. So it would have to be this version here. So that's a shorter way of thinking about it. Well, since this side went up at -3, this side has to go the opposite direction because the multiplicity is 1, and I'm thinking about that graph of 1 over x, where 1 over x one side went up and the other side went down. We're focusing on what's happening near the asymptote, right, near the y-axis. One side went towards a positive infinity and the other side went to negative infinity. So that means they have to go opposite. And the same, for the same reasoning, I can make quick of the work to do over here. Since this multiplicity is 1 that came from 2x minus 1, this 1/2 vertical asymptote came from this factor. Since this side goes down to negative infinity, that means that I'd have to have the opposite happening on the other side of the asymptote. So this side will have to go up towards positive infinity. So I'm going to go ahead and sketch what this side would have to look like because I have to approach both asymptotes. So this side would head up, and then since I have to approach the x-axis, this side would go closer and closer to 0 on this side of the graph. So this is a sketch of this rational function. Again, if I didn't understand this asymptotic behavior, I can always substitute in value. So over here, you could have substituted in, let's say, 2 into the original function, regular or factored version. Factored version would probably be easier. And what would happen is we'd get out some positive number. And that would tell us that it's this piece that's above the x-axis. So it has to be defined. So if we double check our domain, it had to be defined everywhere except for -3 and 1/2, right? So 1/2 was here. So it is defined everywhere. And it did go through our x-intercepts. It does approach each of the asymptotes that we drew. So this is a comprehensive sketch of this rational function. And one of the things that might just be a little bit helpful is when you find vertical asymptotes, is to recognize the multiplicity at that point, that each of those was 1, and so maybe below the vertical asymptote to just do a little sketch, like one side would be up and the other side would be down. So one side would be up and the other side would be down. So we don't know until we graph it which one it'll be, but we do know one side will point up and the other side will point down near that asymptote. And now what you're looking at is the graph that we just drew by hand being graphed on Desmos.com. And it's really just to reinforce that we did draw a graph with the same general shape. We did correctly identify the x-intercept and y-intercept. What you'll notice is missing from the website is the vertical asymptotes and horizontal asymptote because they're not actually part of the graph. It's just a guide to help us sketch the graph by hand. But you'll notice that the behavior does get closer and closer to those asymptotes. So what's great about technology is we can see without having to tediously plug in those values what's happening. As I plug in those bigger and bigger x values, what's happening at the ends of the function towards positive infinity is I'm getting closer and closer to 0. On the other side, I'm getting closer to 0, but from underneath the x-axis. So I'm getting smaller and smaller y values there. And then what's happening near the vertical asymptote, the top ends of the function, well, those y values are just getting bigger and bigger as I get close to -3. And over here, as I get close to -3 on the left side of -3. And then again over here, I'm getting closer to 1/2 from the left as my y values are just heading up. And this time I'm getting closer to 1/2, but from the right side. So technology can just let us confirm really quickly, that what we've done is correct. And it shows us that our techniques for doing this by hand can give us a pretty accurate graph pretty quickly. All right, let's try one more of these. So we'll start by factoring the numerator and denominator. In the numerator, I'll take out a 3x. I'm left with x minus 1. The denominator factors to x plus 3, x plus 3. And I actually want to write the denominator as x plus 3 squared. And then we'll leave the numerator 3x times x minus 1. So this is in lowest terms, nothing cancels. The domain of this function, we look at the denominator, and the only thing I cannot plug in is -3. So we'll go from -infinity to -3 and -3 to infinity. Now to find the x-intercepts, I set the y value equal to 0, or f of x equal to 0. But essentially what I'm doing, if you remember, I'm just setting the numerator equal to 0, because the denominator, if we just multiply it to the other side, it just goes away. And we already have the factored numerator, so that's easier to set equal to 0. So this time I'll get 3x equals 0, or just x equals 0. And then x minus 1 equals 0, so I'll get x equals 1. So my x-intercepts are 0, 0, and 1, 0. To find my y-intercept, remember I let x equal 0. Well, if I let x equal 0, that means the entire numerator will be 0, and the denominator will be 9, so my y-intercept is just 0, 0, which we already had from finding the x-intercept. And then we'll go ahead and find our vertical asymptotes by setting the denominator equal to 0. So our vertical asymptote is x equals -3, because that's the value that makes the denominator equal 0, as we remember from the domain. And let's go ahead and add on, because the multiplicity is 2, it's going to behave like 1 over x squared near that asymptote. So it's either going to be both pointing up or both pointing down near that x equals -3, right? So that's not the y-axis, that's near the vertical asymptote, x equals -3. So either both sides are going to point up or both sides are going to point down. We won't know until we actually put this graph together. And we're going to need to go ahead and find the horizontal asymptote. And that's determined by, remember, the degrees. So since I have an x squared and an x squared, well, I'm going to go ahead and take the leading coefficient 3 over the leading coefficient 1. So my horizontal asymptote is y equals 3. Now, because I have a non-zero horizontal asymptote, I have to potentially find where I intersect it. So if I have to figure out where I potentially intersect it, what I have to do is set the original function. I have to figure out, does f of x ever equal 3? That's what I want to know. Does the function ever equal 3? So I'm essentially setting the original function, that 3x squared minus 3x over that x squared plus 6x plus 9, I'm going to set that equal to 3 and try to solve for solutions. Well, it's really just cross multiplying here. So if I cross multiply, I'll get 3x squared minus 3x equals, this 3 will multiply to all of these, so I'll get 3x squared plus 18x plus 27. The 3x squareds cancel. And if I go ahead and subtract 18x to the other side, I'll get -21x equals 27. So I'll actually get x equals 27 over -21. And let's see, both are divisible by 3 here, so I'll end up getting -9 over 7. So that means that I am going to intersect my horizontal asymptote at the x value -9/7. So the reason why we didn't have to check it on the last one, whether the function intersected 0, well, it's because you already think about that when you think about x-intercepts. So we don't really have to do it twice. So if the horizontal asymptote is something other than the x-axis, we have to check it. So it's not the x-axis, it's the horizontal line at 3. And we have to check, okay, well, does the function, the original function, ever equal 3? Are they ever going to intersect? So we set them equal to each other, and if we get out an x value, then they do. Sometimes you'll end up getting the x's all cancel out, and you don't actually get out a value there. So we're going to take all of this information, and we're going to go ahead and graph it. Alright, so here's all my information, just rewritten, a little bit more condensed. And here's my xy plane, so let's start plotting what we have. We have our x-intercept at 1, 0, and we have another x-intercept and the y-intercept at 0, 0. We have our vertical asymptote at -3. and we have our horizontal asymptote at +3. So I'm going to go ahead and put the factors that each of these came from like last time. So 0 came from the factor 3x to the first. 1 came from the factor x minus 1 to the first. And then this vertical asymptote came from x plus 3 squared, which we already talked about has either both sides pointing up or both sides pointing down. We're not sure yet until we start to piece this together. Alright, and we also know that we're going to intersect my horizontal asymptote at -9/7, which is -1 2/7, right? So it's about right here. So this would be -9/7. So I know I have a point where I'm going to intersect that horizontal asymptote at y = 3 there. Okay, so we're going to have two pieces to this graph. We're going to have one piece on the left side of -3 and one piece on the right side of -3, because that's my domain, everything except -3. Well, I'm going to start with the piece that's on the right side since I have some information over there. Well, because the multiplicity of each of these x-intercepts is 1, I know I'm going to have to cut through the x-axis there. I'm going to have to cut through the x-axis at 0 and through the x-axis at 1. And I also know I'm going to have to intersect this horizontal asymptote. So I'm going to go ahead and fill in this piece. I'm going to go ahead and intersect that value. And then I will continue on and know that I have to cut through at 0. And I also have to cut through at 1, so I'm going to have to turn around. And I'm going to actually have to come up here and approach this asymptote. And then I have to go up here and approach this asymptote. So the right side of -3 is going to have to look something like this. I intersect at -9/7. I approach this asymptote up here, and I have to cut through at 0 and cut through at 1 because those multiplicities are 1. And I have to approach this asymptote. So I have to come up here and I have to get closer to this line. So I know that I can't like turn around and do something crazy and go down because there's no other x-intercepts. So I want to get rid of that. I don't want that to happen. I know that I couldn't just, let's say, after I touch the horizontal asymptote at -9/7, I can't turn this way and approach down here because I don't have another x-intercept. So I know I can only go up here towards +infinity on the right side of this vertical asymptote. And now on the left side of this vertical asymptote, because we know that either both sides point up or both sides point down, since the right side points up, the left side is going to have to point up as well. So I know this is going to happen, and I have to approach the asymptote over here. I know I don't intersect any other times. I only found this one value, so I'm going to only approach it on this side towards -infinity. I'm going to get close to +3 on top of the function. So this is my graph of this rational function that we were given. And to wrap up this problem, here we go one more time on Desmos. So this is a sketch on Desmos, where again you'll notice that the asymptotes are not shown here, but we can see that there is one, especially if we zoom in at -3. So if I pick up here on this value, I guess I'd have to zoom maybe out a little bit and keep heading up to see that I would get closer and closer to -3 on both sides. And both sides are heading up towards +infinity. And then if I come over here and zoom in, I can see my x-intercepts at 0 and 1, and that I just cut through both of those. So it's really small, and they stay kind of close to the x-axis, but it's a sketch. We don't know exactly how low we go in our sketch. We just know that we cut through, and then again, we approach our horizontal asymptote of 3. As I head towards +infinity towards the right. So pretty accurate graph that we did by hand.